Hello everyone, this is Emad and welcome to this episode. In this episode, we're exploring one of the most important breakthroughs in modern artificial intelligence. We'll discover how large language models change the way humans interact with machines, what makes them so powerful, and why AI agents could be the next major step in the evolution of AI. So let's get started.
I want you to try a thought experiment with me for a second.
Okay, I'm ready.
So imagine waking up tomorrow morning, right? You just roll over, grab your phone off the nightstand, and you discover that your computer has, it's already answered your emails for the day.
Oh, wow. That sounds amazing, honestly.
Right. But I'm not talking about those generic automated out of office replies.
Yeah, I'm currently away from my desk ones.
Exactly. I mean, imagine it actually read the context of an ongoing negotiation you were having, and it drafted this incredibly nuanced response. It planned your meetings for the week. It finished the data analysis for that big presentation you were stressing out about. And it even booked your upcoming vacation flights based on, your preferred airlines.
That's a lot.
It also wrote custom integration software for your business. And it did all of this while you were asleep.
You know, it sounds like one of those heavily produced concept videos from a tech conference.
Totally.
Like from a decade ago. The kind with all those sleek animations where, nothing actually works in the real world.
Exactly. Just a few years ago, that was purely science fiction. It was just marketing fluff. But looking at the massive stack of sources we have on the table today, we're talking leaked developer memos, the original architecture papers from Google, the latest API documentation from the front lines of machine learning. This just isn't fiction anymore.
No, it's really not. It is rapidly becoming our reality.
It is. And, when ChatGPT was first introduced to the world, I think millions of people, myself included, believed we had just witnessed the absolute pinnacle of artificial intelligence.
Yeah, it was this massive cultural moment.
Huge, because for the very first time, anyone could just sit down and have a fluid, complex conversation with a machine.
Right, it felt like a destination, like we had finally reached the end of this 70-year pursuit to create a machine that could actually understand us.
But the reality we're facing now, especially when you look at the trajectory of these models in our notes, is that the chatbot wasn't the destination at all.
Not even close.
What if it was just the prologue? Because we're watching a completely new generation of artificial intelligence emerge right now. It doesn't just answer questions, It doesn't just generate text for you to copy and paste.
No, it can make actual plans.
Yes. It can use software, search the internet, synthesize information from completely contradictory sources, and even write and execute its own code to test hypotheses.
And it does all of that with almost zero human supervision.
Which is wild. These systems are called AI agents.
And many researchers in these papers we're looking at argued that agents represent a leap in computing that's equivalent to the invention of the large language model itself.
That is a massive claim.
It is. But if we think about the historical progression here, chatbots were designed to help us think, right? AI agents are being designed to help us act.
Oh, I like that distinction.
Yeah, it's a fundamental shift in utility.
Yeah.
This shift is, honestly, it's easily as significant as the moment standalone computers became networked through the early internet, or, when basic cell phones transformed into app-driven smartphones.
Okay, let's unpack this. Because we really need to understand what exactly makes an AI agent tick. How is the underlying architecture different from the chatbots you and I use every day?
Right.
And why are the world's biggest technology companies pouring tens of billions of dollars into building out the infrastructure for them? Could these autonomous agents actually be the very first concrete step toward artificial general intelligence?
That is the big question.
It is. So in this deep dive, we are going to pry open the black box. We're going to figure out what a large language model actually is at a mathematical level, how it processes language, and why the age of the chatbot was really just a warm-up act.
It's a fascinating trajectory. And to truly understand where we're heading with systems that can act autonomously on our behalf, we really have to look at the era of computing that preceded all this.
We have to go back a bit.
Yeah. We have to look at the decades when AI was, for all intents and purposes, invisible.
The invisible era. I love that term. Because if you talk to the average person, there's this really prevailing feeling that AI just I don't know, fell out of the sky into our laps a couple of years ago.
Like an alien technology.
Exactly.
Yeah.
Like some lab in Silicon Valley just flipped a switch, and suddenly students are writing essays with AI, coders are leaning on AI assistants to debug in real time, and it's practically dominating the stock market.
Yeah, the explosion felt sudden.
But looking at the research timeline in our sources, this didn't just appear out of the ether.
Not at all. For decades, artificial intelligence was quietly evolving. But it was highly specialized, and it was running deep in the background.
So we were using it, we just didn't know it.
Exactly. It was the invisible engine of your digital life. When a streaming service recommended a movie to you with that uncanny accuracy, that was AI.
Right, like how Netflix just always knows.
Yeah. And when an algorithmic feed kept you scrolling for another hour, that was AI. It was detecting fraudulent credit card transactions in milliseconds. It was optimizing global supply chains. It was even helping radiologists identify anomalies in medical scans.
So it was doing heavy lifting.
Absolutely. But despite all of those massive world-altering achievements, the technology remained out of sight. It was dealing with structured data. Spreadsheets, pixels, transaction logs.
So it was incredibly smart, but entirely unapproachable for a normal person. Like, we spent 50 years contorting our own brains to speak the language of the machine.
That's a great way to put it.
First, we had to use those literal punch cards.
Oh yeah, back in the day.
Then we had to learn command line interfaces. And if you got one single character wrong in a massive string of text, what happened? The machine threw a syntax error and just refused to do anything.
It was incredibly unforgiving. Eventually, we layered on graphical user interfaces to make it a bit easier. Right. We learned the spatial logic of windows, icons, and folders. Then we adapted again to the physical gestures of touchscreens on our smartphones.
The pinch and zoom.
Exactly. But in every single one of those paradigms, the human was the one adapting. We were translating our intentions into the very limited vocabulary the machine could actually understand.
And this right here is the paradigm shift that kicked off the current revolution. Large language models represent the exact moment that dynamic flipped completely.
Yes.
Instead of us learning the rigid, structured language of computers, the computer finally learned the unstructured, chaotic language of humans.
And that drops the barrier to entry for complex computing down to absolute zero.
Which fundamentally alters the power dynamic between humans and software.
It's massive. You don't need to know Python or C++ to wield incredible computing power today. You don't need to navigate through 3 sub-levels of a settings menu just to execute a basic command.
You just talk to it.
You just describe your problem in plain, messy, everyday English. And the machine responds as if you were collaborating with a colleague.
It's amazing.
It has democratized high-level processing power for hundreds of millions of people who have never looked at a single line of source code in their entire lives.
But the question we have to answer for you listening is, why was this impossible for so long? Because researchers have been trying to do this forever.
For decades. The dominant approach in computer science used to be what's called symbolic AI.
Right.
Researchers actually tried to manually program the rules of English grammar
Right.
into computers.
That sounds like a nightmare.
It was. They tried to create massive dictionaries and logic trees, and it failed miserably. Because human language is just too context dependent. It's too full of idioms, sarcasm, and exceptions to be hard-coded.
Like, how do you hard-code sarcasm into a logic tree? You can't.
You really can't. The breakthrough only happened when we abandoned trying to teach the machine the rules of language, and instead we built architectures that could discover the statistical patterns of language entirely on their own.
And that brings us to the engine itself. We hear this acronym all the time, LLM, Large Language Model. But going through the architecture breakdowns in our sources, it is wild how counterintuitive the actual mechanics are.
It really defies common sense.
I want to throw out an analogy here for you to think about. Imagine you meet someone who has spent their entire existence locked in a room doing absolutely nothing but reading.
Okay.
They've consumed millions of books, research papers, Reddit threads, legal contracts, poetry, Wikipedia articles. Basically, they've absorbed the sum total of recorded human knowledge.
A lifelong reader.
Exactly. And then you ask them to write a business proposal.
Right. And instead of frantically running over to a filing cabinet to find a specific template for a business proposal, they just draw upon the structural patterns they've internalized from reading 10,000 proposals in the past. They generate a brand new, highly specific response that fits your exact parameters, based purely on pattern recognition.
So let's break down that acronym, because the terminology gets thrown around so much in the media that I think it loses its meaning. Let's start with the middle word, language.
Language is arguably humanity's most powerful invention. It is essentially a compression algorithm for reality.
Oh, I like that, a compression algorithm.
Yeah, it's how we structure concepts, preserve our knowledge, and express complex logic. So, an AI that's built specifically to process language isn't just learning vocabulary words.
It's not a dictionary.
No, it is learning the underlying architecture of human thought. It learns how a premise leads to a conclusion, how tension resolves in a story, and even how a software problem is logically debugged.
Which brings us to the word model, and I was looking at the developer notes here, and it really strikes me how often this specific word gets misunderstood. Even very tech-savvy people often talk as if these models are just highly sophisticated search engines.
It is easily the most persistent misconception in the entire field. An LLM is not a database.
If it's not a database?
It does not have an internal, compressed copy of the internet that it secretly searches when you ask it a question.
So it's not looking things up?
No. It is a mathematical system. It's a massive web of probabilities.
Yeah.
During its training phase, it doesn't memorize sentences. It compresses the relationships between concepts into numerical values, which we call parameters.
So it's a generative engine, not a retrieval system.
Exactly.
That is such a vital distinction for you to keep in mind. It's generating the text on the fly. And finally, we have large, which obviously refers to the scale. But we're not talking about megabytes of data anymore, are we?
The word large barely captures it at this point.
Yeah.
Early iterations of these models, they had a few million parameters, which again are essentially the mathematical connections between concepts.
A few million seems like a lot.
It was back then. But today's frontier models, they have hundreds of billions, sometimes over 1 trillion parameters.
A trillion?
Yes. And they are trained on data sets containing trillions of words. It requires massive data centers packed with thousands of specialized GPUs running at maximum capacity for months just to process the math required to build the model in the first place.
So you combine those three large language model, and you get this massive neural network whose entire purpose is basically to predict what word should come next in a sequence. But here is where it gets really interesting.
Okay.
If the model is just a giant autocorrect, like just predicting the next word, how does it know how to code? Because our sources document this incredible phenomenon where models suddenly developed abilities they were never explicitly trained for.
Yes, these are known as emergent abilities.
Emergent abilities.
And it's a heavily debated topic among researchers right now.
Yeah.
Because no engineer sat down and programmed a specific translation module or a Python debugging module into these baseline models.
Right. There wasn't a guy typing, if asked to code in Python, do this.
Exactly. But because logic, mathematics, and programming languages are fundamentally just highly structured forms of language, the model naturally absorbs their patterns.
Because it read the whole internet.
Right.
Yeah.
So once a model scales up to a certain size, its ability to predict the next token becomes so insanely sophisticated that it can synthesize entirely new software scripts simply because it has mapped the deep logical structure of how code resolves.
I do want to push back on the framing of that, though.
Sure.
When we say the developed abilities, it almost sounds biological, you know? It sounds like cognition, like it suddenly woke up and learned to code.
It does sound like that.
But if we dig into the research papers on these zero-shot capabilities, isn't it true that what we call reasoning or emergent abilities is really just incredibly high-dimensional pattern matching?
Yes.
Like if it writes Python code, it's not because it understands the final goal of the software. It's because it knows statistically what the next line of a Python script usually looks like, given a certain prompt.
That is exactly the debate at the bleeding edge of AI research right now. Are we seeing actual reasoning, or are we just witnessing pattern matching so advanced that it perfectly simulates reasoning?
It's a fine line.
It is. When an LLM solves a complex logic puzzle, it's not experiencing an aha moment.
Yeah.
It doesn't have an epiphany. It's just tracing a high probability path through its neural network.
Right.
But practically speaking, if the output is completely indistinguishable from a human engineer's work, the philosophical distinction starts to matter a lot less to the end user.
If the code runs, the code runs.
Exactly.
Okay, let's get into the actual mechanics of how this math happens, because computers don't read English letters. They don't know what an A or a B is. They only process numbers. So how on earth do we feed human language into a math equation?
This brings us to the foundational currency of all modern AI architectures: the token.
Tokens. If you read any API pricing sheet or any model release announcement from these companies, it's all about tokens.
Everything is tokens.
But the assumption most people make is that one token equals one word. And the documentation makes it very, very clear that is not the case.
No, treating tokens purely as whole words would actually be wildly inefficient for the computer.
Really? Why?
Well, a token can be a whole word, sure, but it is often a fragment of a word. It can be a single character or even a punctuation mark. Most modern models use a specific process called byte pair encoding, or BPE.
Okay, give us an example of how that actually works under the hood.
Let's take the word unbelievable.
Okay, unbelievable.
A human reads that as a single concept, right? One word. But an AI's tokenizer might slice it into 3 separate tokens.
Yeah.
Unbelieve and able.
Oh, it breaks it down into prefixes and suffixes.
Exactly. The brilliance of this approach is scalability. Language is very modular. By learning the prefix un and the suffix able, the neural network doesn't have to memorize every single variation of a root word in the English language.
That makes a lot of sense.
Yeah, it can encounter a completely novel word it's never seen before, break it down into familiar subword tokens, and deduce its meaning mathematically based on the pieces.
Okay, so you type a prompt, and the tokenizer immediately slices your text up into these Lego bricks, and it assigns every single one a unique ID number from its massive vocabulary list.
Yes.
And from that exact millisecond on, the AI is totally blind to language. It is just crunching a matrix of numbers.
It never sees letters again.
But there has to be a physical limit to how many numbers it can process at once, right? We see this discussed constantly in the developer notes as the single biggest bottleneck in the AI industry.
Yes, and that limitation is called the context window.
The context window.
It is the absolute maximum sequence of tokens the model can hold in its active memory while it's generating a response for you.
I've seen this compared to RAM in a traditional computer, but the analogy I find much more intuitive is, imagine reading a really long novel, but you're looking through a tiny hole in a piece of paper.
Oh, that's a good one.
You can only see a few sentences at a time. And if the hole is too small, you might actually forget the beginning of a paragraph by the time you reach the end of it.
Or think of it like driving at night with your headlights on.
Okay, how so?
The headlights only illuminate a certain stretch of the road ahead of you, right? As you drive forward, new road appears in the light, but the road behind you falls into darkness.
Oh, I see.
If your conversation with an AI exceeds its context window, let's say it has a hard limit of 8,000 tokens, the oldest parts of your prompt literally disappear from its active memory.
They just fall into the darkness.
Exactly. It cannot use that older information to predict the next word because it has literally fallen out of the context window.
And this isn't just a software choice by the developers, it's a hard physical constraint, right? Because processing all those tokens simultaneously requires massive amounts of VRAM on the graphics processing units.
Exactly. The memory required to calculate all the relationships between those tokens scales quadratically. This is why models with massive context windows like we're seeing 1 million or even 2 million tokens now are such monumental engineering feats.
But this brings up a massive logical gap that I think we need to bridge for you. If a token is just an arbitrary ID number, let's say the token ID for the word cat is 482913.
Okay.
That number is completely meaningless. It's like a passport number. My passport number tells you absolutely nothing about my personality or my physical appearance.
Right.
So how does a mathematical equation know that the arbitrary ID number for cat is closer in meaning to the ID number for dog than it is to the ID number for spaceship?
This is where we get into the real magic of modern machine learning. Elevating baseline assumptions from just mapping numbers to mapping meaning requires a concept called embeddings.
Embeddings.
Embeddings represent the exact moment where rigid mathematics becomes fluid semantics.
Okay, take us into the latent space. How do embeddings actually capture meaning?
They do it by converting that simple one-dimensional token ID into a highly complex, multi-dimensional vector.
Explain that simply if you can.
Imagine trying to categorize every single object, concept, and emotion in the entire universe using a checklist of thousands of distinct traits.
Okay, like a massive survey.
Exactly. Is it biological or synthetic? Is it associated with royalty or commoners? Is it large or small? Positive or negative?
So instead of cat just being a random ID number, it becomes a coordinate in a space with thousands of dimensions.
Precisely. And in this incredibly vast mathematical space, which researchers call latent space words, that share similar semantic meaning naturally grouped together.
Like constellations of stars.
That's a beautiful way to think of it. The coordinates for doctor, physician, and surgeon form a very tight cluster. The coordinates for laptop and keyboard form another cluster entirely.
So it's essentially a topographical map of human meaning, and the model is just calculating the geometric distance between these coordinates.
Exactly. And the most famous example of this from early AI research perfectly illustrates how structural this actually gets.
Oh, the king and queen example. I love this.
Yes. Researchers discovered that if you take the mathematical vector for the word king, you subtract the vector for man, and you add the vector for woman, the resulting coordinate points almost perfectly to the word queen.
King minus man plus woman equals queen. It is astonishing because it proves the neural network didn't just memorize dictionary definitions.
Not at all.
It discovered the abstract concepts of gender and royalty purely through observing the geometry of human language.
It proves that the model is navigating a semantic space. It understands that automobile and car are pointing to the exact same conceptual real estate, even though they have completely different token IDs.
That is wild. So we have tokens mapped into this multidimensional meaning space via embeddings. The model understands the constellation of concepts, but language isn't just a bag of isolated words, right? The order matters. The context of the sentence dictates the meaning. How does the AI read a whole paragraph and know which specific words it needs to focus on? Because looking at the timeline in our sources, before 2017, this was the exact thing that kept AI completely stuck in the mud.
It was the critical bottleneck for the whole industry. Older neural networks, like recurrent neural networks, they process text strictly sequentially, word by word.
Like reading left to right.
Exactly. But the problem is what engineers call the vanishing gradient, or the long-range dependency problem.
Which means what?
It means by the time the model reached the end of a long sentence, its mathematical memory of the very first word had severely degraded.
Oh, it's like trying to follow a really complex legal argument, but you can only remember the last 5 words the lawyer said. You would lose the plot entirely.
Exactly.
So how did the industry finally solve it?
In 2017, a team of researchers at Google Brain published a paper that completely rewired the trajectory of computer science. The paper had this deceptively simple, almost poetic title: Attention is all you need.
Attention is all you need. That's iconic.
It really is. And it introduced a brand new architecture called the transformer.
And we see the word transformer everywhere now. It's literally the T in ChatGPT.
Exactly.
But digging into the architecture in our sources, what the transformer actually does is allow the network to process every single token in a sequence simultaneously rather than sequentially. And the engine that drives this is the attention mechanism.
Yes. The attention mechanism allows the model to look at a token and instantly ask, which other words in this entire sequence provide the context I need to truly understand my own meaning?
I was reading through the math of how this actually works, and the sources break it down into 3 specific matrices: query, key, and value.
Yes, Q, K, and V.
And if I'm understanding this correctly, it's not just a simple database lookup. It is massive matrix multiplication. Every single token is assigned these 3 roles simultaneously.
That's a brilliant way to conceptualize it. Every token generates a query vector, which is what it's looking for. It generates a key vector, which is what it contains, and a value vector, which is its actual semantic weight.
Okay, let's use a practical example to make sense of the math for the listener, because it's pretty heavy. Let's take the word bank.
Good example, it's highly ambiguous.
Right. If the sentence is, the bank approved my mortgage, the token for bank generates a query asking, am I a Riverside or am I a financial institution?
Right.
The token for mortgage generates a key that essentially says, I am related to finance and loans. So the math calculates the dot product between the query of bank and the key of mortgage. They align perfectly, and that creates a massive attention score.
Exactly. That high attention score dictates that the model should pull the value from mortgage and blend it directly into the meaning of bank, solidifying its context as a financial institution.
In real time.
Yes. And it does this calculation across multiple heads of attention simultaneously. One attention head might be looking for grammar and syntax, while another one is looking purely for semantic meaning.
There's another classic example in the notes that shows why this is so revolutionary for actual logic.
Which one?
The sentence is, the trophy didn't fit inside the suitcase because it was too large.
Oh, yes. The vinaigrette schema.
Right. So to a human, common sense tells us the word it refers to the trophy. The trophy is too large. But a machine has no physical common sense. It has never held a suitcase.
No.
How does it know it doesn't refer to the suitcase?
Through self-attention. The model compared the query of it against the keys of both trophy and suitcase. Because the model has processed trillions of text sequences during its creation, it has learned the statistical reality that containers, like suitcases, are meant to hold objects like trophies. And when things don't fit, it is usually the object that is described as too large. So the attention mechanism assigns a higher statistical weight to trophy, dynamically resolving the ambiguity in milliseconds.
That is just incredible. But this leads to a massive question. If the model is calculating query, key, and value matrices across thousands of dimensions for thousands of tokens in a context window all simultaneously, the sheer volume of arithmetic is unfathomable.
It is astronomical.
So how on earth does a chatbot generate a response on my phone in half a second?
This touches on the fundamental divide in machine learning operations. To understand why it's so fast on your phone, you have to understand the difference between the two distinct phases of a model's life cycle: training and inference.
Right. Training is basically the kitchen where the recipe is painstakingly created, and inference is just cooking the meal for the customer.
Exactly.
Let's look at training first, because the scale described in these developer notes is staggering.
Training is arguably the most computationally intensive undertaking in human history.
That's not an exaggeration.
Not at all. It takes months, massive clusters of tens of thousands of GPUs, and literally gigawatts of electricity.
Wow.
The model starts with completely randomized parameters. It does absolutely nothing. It is fed a sequence of text, it tries to predict the next token, and it almost certainly gets it wrong.
Naturally.
And this is where backpropagation comes in. It compares its wrong guess to the actual correct word, calculates exactly how wrong it was, which is called the loss function, and then it mathematically walks backward through its billions of parameters, slightly adjusting the weights so that next time it'll be a tiny bit closer to the right answer.
Imagine standing at the top of a mountain in dense fog, trying to find the absolute lowest point in the valley. You can't see the bottom, so you just take a step in whatever direction slopes downward the steepest. That is gradient descent.
That's a perfect analogy, and the model does this trillions of times. It takes these microscopic mathematical steps, constantly adjusting its internal structure until the prediction error is minimized.
So that takes months and costs hundreds of millions of dollars. But once that optimization is completely done, the model is baked. The learning stops.
Yes.
And we enter the inference phase.
Yes. During inference, that multi-billion-dollar supercomputer is no longer updating its parameters. The weights are completely frozen.
So it's not learning anymore.
No. When you send a prompt, the model is simply executing the math forward. It converts your text to tokens, runs them through the transformer layers, calculates those attention scores we talked about, and outputs a probability distribution for what the next token should be.
And then it just picks one.
It picks one, adds it to your prompt, and runs the entire cycle again. This is called autoregressive generation.
Autoregressive. And because it's not learning, just executing static math, it can do this at blinding speed.
Exactly.
But wait, if it's just selecting the mathematically most probable next token, why doesn't it give me the exact same robotic answer every single time I ask the exact same question?
Because of a parameter called temperature.
Temperature.
During inference, engineers can actually inject a controlled amount of randomness into the selection process.
How does that work?
If the temperature is set to 0, the model will always pick the absolute highest probability token every single time. It will be highly factual, but very, very repetitive.
This sounds boring.
It is. But if you turn the temperature up, the model might occasionally select the second or third most probable token. This introduces variance, creativity, and a much more natural cadence to the text.
Which is why when I ask it to write a poem and they've cranked up the temperature, it feels so incredibly human.
Exactly.
And this brings up a point that I think every single person using these models struggles with at some point. When you adjust those parameters and it produces a highly empathetic response, like when you explain a really tough situation you're going through and it says, "I understand how difficult that must be," it really feels conscious.
It does.
If it can synthesize completely novel logic, does it actually understand us?
From a strictly technical perspective, no, it doesn't. This is a classic philosophical debate in cognitive science. It closely mirrors John Searle's Chinese room thought experiment. The AI is manipulating symbols perfectly, but without ever understanding the meaning behind those symbols. It doesn't have an internal experiential model of reality.
So it's a stochastic parrot.
Yes, a wildly sophisticated one, but a parrot nonetheless.
I was reading a critique in the sources that argues these models are like immensely talented actors.
Oh, I like that comparison.
Yeah, an actor can deliver a devastating monologue about grief, crying real tears on stage without actually experiencing that grief in reality. They have just mastered the expression of the emotion.
Right.
AI has mastered the linguistic expression of understanding without possessing even a spark of actual cognition.
And that illusion of intent is so powerful that it physically tricks our biology.
It does. If you've ever found yourself typing please and thank you to an AI, you are experiencing this firsthand. I do it constantly, and I know exactly how the matrix multiplication works.
We all do it.
It's because the simulation of human language triggers our deep-seated evolutionary response to personify anything that communicates with us.
And because that simulation is now robust enough to drive actual, tangible economic value, we are seeing an absolute explosion of competition in the space.
Oh man, looking at all these developer notes, this isn't just a unified race to build the biggest brain. There is a massive ideological and architectural split happening right now.
A very distinct split.
When you map out the current ecosystem based on these white papers, you don't just see a list of products. You see distinct philosophical approaches to the future of computing.
Let's define those approaches. The first is what we might call the closed ecosystem megaliths.
That's primarily OpenAI and Google, right?
Yes, they are building massive proprietary models hidden safely behind APIs. OpenAI's GPT models are incredibly versatile. They're designed to be the ultimate enterprise generalists.
Right, the Swiss Army knife.
Exactly. And Google's Gemini is deeply integrated into their existing ecosystem, so Docs, Drive, Android. And Gemini focuses heavily on native multimodality, processing video and audio just as naturally as text.
But then you read the white papers from Meta and Mistral, and they are running a completely different playbook.
Very different. That is the open weights rebellion.
Open weights.
Yes, Meta's Llama models and the European startup Mistral, they have chosen to release the actual underlying weights of their highly capable models for free.
Which is a direct strategic attack on the business models of OpenAI and Google.
It's brilliant strategy. If you give away a highly capable model for free, you basically commoditize your competitor's primary product.
And it completely changes how society uses AI. Let me give you an example from the sources. If I'm a hospital administrator, I cannot legally send sensitive patient data to an OpenAI server to be processed, right?
Because of IPEA and privacy laws.
Exactly. It's a massive security risk. But because Meta's Llama is open weights, I can download it, install it on a secure, completely air-gapped server in the hospital basement, and run advanced AI analysis with total data privacy.
The democratization of the weights ensures that AI isn't solely controlled by 2 or 3 tech conglomerates.
Which is super important. And then you have the third ideological approach, which has really shocked Silicon Valley recently.
The highly specialized reasoning challengers.
Like China's DeepSeek. This was a massive revelation in the sources. The prevailing assumption was that to get smarter AI, you just had to throw more billions of dollars at larger training clusters.
Right, scale is all you need.
But DeepSeek proved you could compete at the absolute frontier with a fraction of the budget, just by radically optimizing the architecture and focusing heavily on reinforcement learning for math and coding.
Yes, but I know you want to push back on how we actually define their success in reasoning.
I do, because the marketing around these new models focuses heavily on the word reasoning. You know, they show the AI outputting its quote-unquote internal monologue before it answers you.
Right, the thinking phase.
But looking at the technical breakdowns, is it actually reasoning? Or is it just doing more computational search at inference time? Because if you slightly alter a classic logic puzzle to trick it, it often still fails because it relies on the pattern of the original puzzle.
That is a highly valid critique. What they are doing is called test time compute.
Test time compute, what does that mean?
Instead of generating the first answer that comes to mind, the model is trained to generate multiple potential paths, critique its own paths, and then output the final result.
Oh, so it double checks its work.
Sort of. It mimics human system 2 deliberate thinking. But fundamentally, it is still auto-regressive pattern matching. It is just doing it in a loop before finally showing you the result.
It's fascinating. But as we adopt this massive ecosystem of models, we really have to look closely at the cracks in the mirror. Because despite all this architectural brilliance, these models have severe structural limitations.
Very severe.
Let's talk about hallucinations, because this is where the generative nature of the LLM becomes an actual liability.
The term hallucination is heavily used, But it simply means the model generates information that is completely false, yet it presents it with absolute grammatical confidence.
It's a very confident liar.
Exactly. It will invent scientific papers that don't exist, make up historical dates, or fabricate software libraries.
There's that incredibly famous anecdote from the sources that perfectly illustrates why this happens. 2 lawyers in New York used ChatGPT to write a legal brief.
Oh, this story's wild.
Right. They asked it for case law supporting their argument. The AI confidently provided summaries of several federal court cases, complete with citations and docket numbers. So the lawyer submitted it to the judge.
And what happened?
The problem? None of those cases existed. The AI made them up entirely.
And they made the classic mistake of treating a generative engine like a retrieval database.
Yeah.
The model didn't lie to them maliciously, though.
No.
It doesn't have a concept of truth or falsehood. Its only objective, mathematically, is to minimize the loss function by predicting the next statistically probable token.
Right, so if a docket number usually follows a case citation in its training data, it will just generate a statistically plausible sounding docket number, regardless of whether it corresponds to physical reality.
Exactly.
That is terrifying if you are integrating this into automated workflows.
It's a huge risk.
And there is another major technical limitation highlighted in the sources regarding memory degradation. We talked about the context window earlier, right? The headlights on the car.
Right.
But even if you have a massive context window of, say, 100,000 tokens, the models still suffer from what's called the lost in the middle phenomenon.
Yes, this is a well-documented issue. Empirical testing shows that if you hide a specific fact in a massive document and ask the AI to find it, it performs exceptionally well if the fact is at the very beginning or the very end of the document.
Like the primacy and recency effect in human memory.
Exactly. But if the fact is buried deep in the middle, the attention mechanism often fails to weigh it properly and the model misses it entirely. Its contextual memory sags in the center.
So you can't just dump a 500-page PDF in there and expect it to catch every tiny detail.
No, you really can't.
Furthermore, they lack physical grounding. This ties back to what researchers call Moravec's paradox. We can build an AI that can pass the bar exam, write a symphony, and debug complex server architecture. But we struggle to build an AI that has the common sense of a toddler when it comes to understanding how the physical world works.
Because a toddler understands physics through sensory experience. They know that a glass will shatter if it's dropped because they have seen it, they've heard it, and they've felt it.
They have real-world data.
Right. An LLM only knows that the token glass is statistically associated with the token's fall and shatter. It has no causal model of the universe.
So we have these brilliant, flawed, hallucinating, highly capable language engines. But we started this entire deep dive talking about AI agents.
We did.
We said the chatbot was just the prologue. So what happens when we take these LLMs, recognize their limitations, and wrap them in completely new architectures that allow them to stop waiting for our prompts?
This is the transition from generative AI to agentic AI.
Agentic AI.
An agent takes the core reasoning engine of an LLM and gives it a stateful existence, long-term memory, and most importantly, access to tools.
Let's break down tool use. Because an LLM isolated in a server can't do anything but output text. It's trapped.
Exactly.
But if you give it an API connection to a web browser, a code interpreter, and your calendar,
suddenly the text it generates isn't just an answer for a human to read. The text becomes an executable command.
oh, that's a huge shift.
It is. The agent can write a Python script, run it in a sandbox, see the error message if it fails, realize its mistake, rewrite the code, and run it again until it actually works.
Yeah.
It operates in a continuous feedback loop.
It's moving from a single prompt and response paradigm to an autonomous workflow.
Exactly.
We are also seeing the integration of true multimodality. We're essentially giving the agent eyes and ears.
Right. Instead of just parsing text, native multimodal agents process pixels and audio waveforms directly in their neural network.
So what does that look like in practice?
Well, you can show an agent a live video feed of a manufacturing line, for example. And it can visually identify a microscopic defect in a part, cross-reference it with the engineering schematics, and autonomously email the supplier to order a replacement.
All without a human telling it to do so.
Exactly.
Which brings us full circle to our opening scenario. A chatbot can give you a list of hotels in Tokyo, but an AI agent acting on your behalf can log into your account, navigate the booking website, use your credit card, block off the dates on your personal calendar, and draft a complete itinerary for your family.
It bridges the gap between digital reasoning and digital action.
And this rapid development inevitably points the research community toward the ultimate defining goal of the field.
Artificial general intelligence, or AGI.
AGI,
Yeah.
the idea of a system that possesses human-level, highly flexible intelligence, a system that isn't just trained on existing data, but can actually discover novel scientific breakthroughs, learn entirely new domains from scratch, and generalize its knowledge across completely unrelated fields. Whether the current transformer architecture can scale to AGI, or whether we need an entirely new paradigm, the pursuit of it is reshaping the global economy right now.
It is the most ambitious engineering project in human history.
So, what does this all mean for you? We've journeyed from arbitrary token IDs to high-dimensional latent space, through the matrix multiplications of the attention mechanism, all the way to autonomous agents executing logic loops in the real world.
It's a lot to take in.
It is. But as we look at this trajectory, the real question isn't just how computationally powerful these models will become. The real question is, how will human society change when we live and work alongside them every single day?
It fundamentally forces us to reevaluate the utility of our own intelligence.
Exactly. But to truly understand the velocity of where AI is heading and how we might adapt to it, we have to look back at the origins of this pursuit.
We have to look at the past.
Because the story didn't start with the Transformer in 2017. It started much earlier with a completely different set of assumptions about how machines might actually learn to think.
And that history is filled with immense hubris, spectacular failures, and quiet breakthroughs that set the stage for everything we just discussed.
And that is exactly what we are going to explore in our next deep dive. We are traveling back in time to the 1950s. We'll look at the original Dartmouth conference that coined the term artificial intelligence, the devastating periods known as the AI winters, where all the funding dried up and the dream almost died,
Those were dark times for the field.
and the miraculous, stubborn persistence of neural network researchers who eventually proved everyone wrong.
It is a phenomenal story of scientific resilience.
Until then, I want to leave you with one final thought to mull over. As agentic AI begins to seamlessly take over the logistics, the coding, the scheduling, and the data analysis of our daily lives, what uniquely human skill will become the most valuable currency in the world? When a machine can effortlessly do all the technical heavy lifting, what is the irreplaceable value that you bring to the table? Think about that, because this is only the beginning.